Hi everyone. So today I'm going to give a lecture of the topic transfer learning or domain adaptation. So what is transfer learning? So currently we are good at training supervised machine learning models, no matter the inputs are images, sentences, or label predictions from large amount of label data. However, our model still lack of the capability to generalize to conditions where they are different from the ones encountered during the training. So the ability to transfer knowledge to new conditions is generally known as transfer learning. So here is a figure of the traditional machine learning. So you can see in the classic supervised learning scenario of machine learning, if we intended to train a model for some task A, we assume that we are provided with label data for the same task and domain. So we can see the task and domain of the training and test data of model A is the same. We will later define in more detail what exactly a task or a domain are. So we can now train a model A on this dataset and expect it to perform well on unseen data for the same task and domain. On another hand, when given data for some other task B, we will still require again label data for the same task or that we can use to train a new model B, so that we can expect it to perform well on this data. So these traditional supervised machine learning algorithms will break down when we do not have sufficient label data for the task we care about to train a reliable model. So for example, for the task B, you can see if we do not have enough training data, the model B probably will not perform well on the test data due to the lack of label issue. So for the transfer learning, so here is a figure for transfer learning. Transfer learning allows us to deal with these kind of scenarios by leveraging the already existing label data of some related task or domain. So you can see we can store, we can kind of like transfer this knowledge gained in solving the source task, which is the left, the green one. We call it as a source task to solve the target task, which is the red one, and apply it to our problem of interest. So in practice, we want to transfer as much knowledge as we can from the source setting to our target task. So this knowledge can be on various forms depending on the data. It can be general words people use to express their opinions. It can be objects, which is composed to allow us to more easily identify the novel objects. So yeah, this kind of knowledge can be various. So here is some transfer learning terminologies we will define first. So you can see first the task or domain is machine learning task, is any machine learning task that can be solved by learning the underlying data distribution. So for example, if we want to classify, we want to do object recognition to classify image of cat or dog. So this is so-called like animal binary classification task. So this can be called a task or domain. So for source domain, so source domain is which one contains rich label information. So in our previous figure, it's referred as the domain A or the left one. So for target domain, it contains limited label information. So target domain is which we care about. Due to the lack of label issue we mentioned before, we cannot directly train a supervised machine learning model on the target domain. So that's why we are trying to utilize the label-rich source domain to get some transferable knowledge and then train a reliable model for the target dataset. So the goal of the transfer learning, you can say here, is ability to apply an algorithm trained in one or more source domains to a different but related target domain. So yeah, you can say the source domain and target domain should be similar or related to get the transferable knowledge. And here I list some example of the transfer learning application in the real world. So first is for in the computer vision area, when we do the object recognition, you can see there are two different domains. So the model might overfit due to domain difference. You can say for the first domain, for first vision domain, the domain 1 has easily accessible label information we can utilize to recognize the object. But you can say domain 2 has more complicated background information in the domain. So you might think that the two domains look the same, the source domain, but the source domain may still contain bias, which is imperceptible to humans, but which the model will overfit. Yeah, for a human, you may say, oh, it's really easy to identify from those two domains, to identify object from either domain. But for the model, it might cause the overfit, cause overfitting because of the domain difference. And the second application is in the NLP area, which is different text types may cause distribution difference. You can see here we have two different texts from different sources. The left domain is some news data, and the right side is social media messages. So you can see, even though the short sentences may extracted from different sources, so they will, for example, use different kind of sentences or phrases to express the same opinion, which will cause the domain difference. So for example, if we want to train a sentiment analyzer on the news data and utilize the domain adaptation techniques to apply it to the social media messages, so yeah, we have to do some bias correction, for example, to achieve this goal. And the third application is also for NLP, called product review. So you can say for different type of products, the people will use different words or phrases to express the same opinion. So for example, for the Amazon product review, for different product type, you can say book versus blender. Even if the user expresses like same positive opinion, but you can say the words and the phrases uses in the review, in the product review, would be kind of different, even they express the same opinion. So in this case, we can still apply the transfer learning knowledge to utilize the transferable knowledge learned from the label-rich products. So for example, if Amazon has just released a new product, so we can barely collect any label information, right? Because it's just newly released product. So if we want to do some sentiment analyze work on the new product, it's very hard to directly train on it due to the limited label. So that's why we can use some similar previously released product which have already collected enough label information and get some transferable knowledge from the previous products, right? So that's kind of one of the applications of the transfer learning. So here is more detailed definition of transfer learning. So the domain D consists of a feature space X and a marginal probability distribution Px over the feature space. So given a domain D, a task tau consists of label space Y and a conditional probability distribution Py given X, which is learned from the training data consisting of pairs Xi, Yi. And given a source domain DS, a corresponding source text tau-s as well as a target domain dt and a target task tau-t. So the objective of transfer learning is to enable us to learn the target conditional probability distribution Pyt given xt in the domain T with the informed gained from with the information gained from domain S and target S. So given above definition, the condition of the transfer learning can be broadly divided into 4 ways, which we will illustrate the following using the document classification example. So here for these 4 conditions, we will just simply use a binary document classification as an example to illustrate the condition. So the first condition is the x not equal to xt, which means the feature spaces of the source and target domain are different. So in the document classification task, so if the documents are written into different languages, so in the NLP, this is generally referred to as a cross-lingual adaptation. Yeah, so of course, if the documents are written into different languages, their feature space wouldn't be the same. So, for example, if you want to use some backup words method to build a vocabulary, yeah, you definitely have different vocabulary, which can result different feature space, right? And the second condition is the marginal distribution of the source and target domain are different. So still using the document classification task, which means the documents can discuss different topics, so which can result to the marginal probability distribution difference. So for example, even if they are written in the same same language, but they discuss different topics. So you can say this will result in the different marginal distribution, which also called data distribution for those 2 domains. So the first 2 conditions are most common in the transfer learning scenarios. And the third one, the label spaces between the 2 tasks are different. So this is simple. For example, if documents need to be assigned different labels in the target task, so which means for the source and target domain, they have different target label, which means they are predicting different targets or different classes. And the last one is the conditional probability distributions of the source and target task are different. So in practice, this scenario usually occurs with the third scenario. So you can say, if for example, if they have different labels, of course their conditional probability wouldn't be the same, like in most cases, right? So it's very rare for 2 different texts to have different label spaces but have the same conditional probability distribution. So yeah, so here are the 4 conditions for the transfer learning. And next, I will give an example method proposed by some researcher before for the transfer learning methods. So this one called joint distribution adaptation, which is proposed in 2013, is one of the most well-known traditional transfer learning methods. So first, this as we mentioned, the 4 conditions. So this paper have 2 condition assumptions. First one is they have different marginal distribution, and then the 2 domains have different conditional probability. So they propose the method to jointly adapt both the marginal and conditional distributions in a principled dimensionality reduction procedure. So the goal is to adapt the joint distribution by a feature transformation matrix T so that the joint expectations of the feature X and label Y are matched between domains. So the dimensionality reduction methods can learn a transformed feature representation by minimizing the reconstruction error of the input data. So this paper or this method choose the principal component analysis, which called PCA, for the data reconstruction. So here you can see X is the input data matrix, which is a M by N dimensional matrix. Here M is the dimension and N is the data size. A is a transformation matrix we want to learn, and M is a dimension of the latent feature space. So normally K will less than N. Sorry, K is the dimension of the latent feature space. So you can say for the dimension reduction method, it will reduce the dimension of the original data to some latent feature space K. So that's why K often less than, the size of K less than the original size N. So that's why the PCA is also called the dimension reduction method. And next, so even though the PCA is introduced, the distribution difference between the two domains is still significant. So to reduce the distribution difference, so this method adopts a distance measurement mechanism called the maximum discrepancy to reduce the distribution difference. And here, you can say M0 is calculated to reduce the marginal distribution difference. Yeah, M0. And so here is a maximum discrepancy distance, and MC is calculated to reduce the conditional distribution difference. Here C represents the class label. So you can say for each class label C, we will calculate a matrix C, a matrix to reduce the conditional distribution or conditional probability difference. And this, so this is optimization function. So this method aims to minimize the differences in both marginal and conditional distribution at the same time. So to reduce the marginal and conditional distribution difference jointly, the method JDA method proposed an iterative learning process similar to the EM algorithm, using the pseudo target labels to improve the labeling quality until convergence. So according to the constraint optimization theory, the objective function is denoted as the Lagrange multiplier. So by setting the partial derivative A to 0, we can obtain the generalized agent decomposition equation. So finding the optimal adaptation matrix A is to solve this equation for the k smallest agent vectors. Yeah, as I mentioned before, the k is just the latent space dimension, right? So here is how we find the latent feature space to minimize the joint distribution difference. And here is the pseudocode. So I will not go into the detail. So if you are interested in the detail of algorithm and the pseudocode, so you can refer to the paper. So here is a paper link and also a sample of the Python code. And next, I will give an introduction of another transfer learning, which is pretty novel, and this concept is kind of like proposed in recent years, which is called future learning or meta learning. So compared to the traditional transfer learning, the traditional transfer learning is often transferred from one task to another task. So as you say, as you have seen before, there's often only one source domain and only one target domain. And however, for the recent future learning, it's often transferred from multitask to multitask. So here I will give you some concept of the future learning. So considering the task in the figure, thinking you are asked to distinguish whether the test drawing belong to Barque or Cezanne. So with these very few label samples, we still can accomplish the task using previous knowledge, right? For example, we have seen a lot of drawings from different artists before. So then from those previous experience, we learned. So we have learned the drawings with a similar shape, color, or design are highly possible belongs to the same author. So you can see all of those prior knowledge learned from different tasks in our previous life can be utilized to help the model quickly adapt to a new task with very few label data instances for each class. So we call this a future learning, right? So you can say instead of using only one source task to do the transfer learning, so this kind of future learning can utilize the whole task we learned in our entire life to infer our target task, right? So that's basically the difference between the traditional transfer learning and this future learning. So here is the intuition behind future learning. So here is a problem statement. So different with the supervised learning, which only have one dataset D, the future learning tries to use more meta-train set D meta-train as a prior knowledge in order to quickly adapt to new tasks with very few labeled data points. So the prior knowledge is presented as a set of tasks. So in this case, you can think each of those datasets, no matter our target dataset D or the metaset D meta-train, as a five-way classification, a five-way image classification task. So, and for each of the tasks, there's only one label data instances available. So we call this as five-way one-shot learning. The goal of the meta-learn is trying to utilize a large amount of meta-train set. So those are the meta-train set. It can be hundreds, thousands, right? The goal of the meta-train is just trying to utilize a large amount of the meta-train sets to help predict the classification task in D. So you can say that D is our target classification task. It can be one, or it also can be multiple target tasks. So you can say here they have very similar task structure. They are all five-way classification, and each classification have one label data, right? So you can say here in the green box, you can think those are the training data, and in the blue box, those are the test data for each task. So you can say here, each task will have their own training data and test data. So imagine you are given a classification task D only. If we directly train a classifier on D, the performance will not be promising, right? Because there's only one label data for each class. So that's why the future learning method is trying to use the D meta train to form some related but different classification tasks to help the model learn some prior knowledge before the target task did. So one very important feature here is there's no overlapping class between the D meta-train and our target classification D. So in the example of the mini ImageNet classification task, the target dataset contains, you can see, flower, dog, lion, worm, and bow. So those classes will not be available in the meta-train stage, which means they will not available in the D meta-train, D1, D2, D3, Dn, which means the model will never learn the target task directly because there's no such label, such class available in the D meta-train. So the model will not directly learn the task as a traditional supervised model do. And this is a high-level objective function for meta-learning. So you can see in the meta-train stage tries to learn the model parameters on a bunch of meta-train tasks. The parameters data can be used as a prior knowledge in the meta-testing stage for our task. With very few label meta-test data, you can say the very few label can be one label data for each class. They can be two label data from each class. And in this few short setting, there will be like no more than 5 label data for each of the class. So that's why we call it a few short learning. It's very few. So with very few labeled meta-test data, the model can learn the 5 quickly. So here each meta-train set DI will be further divided into D training and D test for each class, serving as a training and test set as normal supervised learning. You can see for each task, they still have the training and test data. So, so to distinguish with meta-train and meta-test set, we call them as support and query examples. So the support set are shown in the green box, and the query set are showing in the blue box. So they are actually for training and testing purpose for each of the tasks. So so you can see here, each task contains the whole process of training and testing, which is different from other pre-training method, which only contains the training process. So that's why the future learning is also called learning to learn. Since you can see the future learning will learn from the whole learning process, from training to test, instead of only learn from the training process. So that's the one big difference from the traditional supervised learning or the transfer learning. So we already know the future learning framework in the previous slides. So the next question is, what method we can use to learn the classification model? So basically there are 3 kinds of methods: the model-based, the metric-based, and the optimization-based. So here we will select the metric-based method as an example to illustrate the future learning inference process, since they are simple and easy to understand, but they also work well. So yeah, you can see here one of the simple and effective way is using the distance to compare the similarity and dissimilarity between the support and query samples. So thinking about the k-means, k-n, those methods try to learn a latent feature space where the samples with the same label will be close to each other and vice versa. So, so next I will introduce most well-known metric-based future learning method, which is called prototypical networks. So first, what is a prototype? So consider the whole procedure of the k-means, aiming to partition n observations into k clusters, in which each observations belong to the cluster with the nearest centroid, which is mean. So the first step is to randomly initialize k centroids and assign the observations to its nearest centroids. And then we generate the new k centroids by calculating the mean of each cluster. And we repeat this process again and again until the centroids do not change. So you can see here the centroids or the mean will serve as a prototype. So that's the definition of the prototype. It often can best represent each of the class. So, and here is a illustration of the prototypical network. So this figure shows the inference stage of a three-way 5-short learning, which means we will have 3 classes for each task, and each task will have 5 labeled instances for each class. So after the input images are embedded into the latent feature space shown in this so after the input image are embedded into the latent feature space shown in this figure, so C is a prototype. The C1, C2, C3 are the prototype calculated by averaging the support samples. So which is the support sample is denoted by the round points in different colors for different classes. So the goal is just to minimize the distance between the X is the query sample, and the corresponding prototypes. So for example, if the true label of X is class 2, then we want to reduce the distance between the X and the class 2 in the latent feature space. So we need to note here the label of query samples X are known during the training stage and unknown during the testing stage. And the label of the support samples are known during both stages. So that's why it's called future learning system. We are trying to infer the label of the query sample with limited label support samples. And so here is a flow chart of the prototype network. So you can see here for each episode. For each episode, we will have a task, right? So for each of the tasks, we will have the labeled support sample and the labeled query sample. It will be forwarded to a embedding module to get the latent feature space. And in this latent feature space, we calculate the distances for the support for the prototypes. We calculate distances between each query and the prototypes, and we're trying to minimize the distances for the labeled query data, right? Using the Euclidean distance to calculate distance, and then use a softmax function to do the model update to minimize the distance between the query and the prototype and its belonging prototypes. So you can see here we will have a lot of like thousands of episodes to update our embedding module. So the goal is to learn such a latent feature space where the instances, where the images from the same classes will be close to each other, and the images from different classes will be far from each other. So you can see the model, embedding model, will be updated like for after each episode. So you can see here is a pseudocode of the loss computation for each episode. So as we learned before, so each episode contains dataset D, which can be further divided into support and query set. So the support samples and their label information are used to calculate the prototypes C, right? So I mentioned before, C is just the mean of each of the instances belong to the same class. And the query samples and their label information are used for loss computation in the training stage. And in the testing stage, the query sample label are unknown and are inferred through the distance between the prototypes in the latent feature space. So here the fx is the function to embed the input data to the latent space. The paper, so this prototypical network paper just uses CNN to encode the image data into embeddings. And here is a paper link of a prototypical network and a sample Python code. So for next lecture, I will show how to do some practice using the prototypical network code, and then you will also have some homework solutions to solve based on this prototypical network code, sample code. Yeah, so basically that's all for today.